All right, ladies and gentlemen, welcome back. This is Mr. Doolin again. Thank you for tuning in. This is part 2 of free energy. Hopefully you got through part 1 all right. You survived, you tuned in. Way to go. So what we're going to do now is we're going to continue on with defining entropy in terms of this free energy or this spontaneity prediction. One thing that we do know about entropy is a state function. All right, so again, it's very similar to that enthalpy, that delta H value that we've been calculating, to where we know that it's only the difference between reactants and products that makes a difference, and we can apply Hess's law to our entropy calculation. So again, I'm going to use the combustion of hydrogen as my working example here. And so I've got 2 moles of hydrogen, 2 moles of water over here. I think I'm making this a liquid. And then it's an exothermic reaction that's going to release 570 kilojoules per mole. All right. So since it's an enthalpy function or a state function, we understand we've got these absolute entropy values, and I'm going to go ahead and put them down here. So for hydrogen, it's 131 joules per mole dot Kelvin. For oxygen, it's 205 joules per mole dot Kelvin. For water, as a liquid, it's actually 70 joules per mole dot Kelvin. And what I challenge you to do is that you should be able to use those values and actually come up with an overall delta S of the reaction. So go ahead and do that. All right, and so what we come up with here is I just went ahead and gave you the answer to where it's negative 327 joules per mole dot Kelvin. Now, a lot of you right now, if you watch question number or part 1, you're looking at this going, well, wait a minute, Mr. Doolin, you said hydrogen combustion is a spontaneous process. It happens, and it does, right? But the thing that we need to look at, and you could have also done this, maybe some of y'all caught it in the first lecture, where I've got 3 moles of gas on my reactants, I've only got 2 moles of gas in my products. I did predict an entropy decrease here. And so the question becomes, if the entropy of the reaction is actually going down, then why the heck is this thing spontaneous? And so now we're going to start getting into why we've looked at enthalpy, right? So, at a constant pressure, what we do know is that our delta H value for our reaction is actually equal to our heat gained or heat lost, right? At a constant pressure. And so what that means, remember with endothermic, exothermic, we're defining where energy is going, whether it's going into my reaction or being released from my reaction. And so I have this relationship where I've got a negative delta H for my reaction is equal to a positive delta H for my surroundings. And so all we're saying, again, this is going that first law of thermodynamics, like law of conservation of energy. If my reaction is going to lose energy, the surroundings are going to gain it, and vice versa. So in this particular case, the way that would work out, my delta H of a reaction is actually negative 572 kilojoules per mole. And again, I know that because my energy is a product here, it's being produced, it's being released, which means that my delta H for my surroundings is actually going to be a positive value, 572 kilojoules per mole. And again, based on the law of conservation of energy, those values are equal but opposite signs, because one's gaining and the other one is actually losing. All right? So let's take a look at a couple of things. We know the delta S of reaction is actually equal to negative 327 joules per mole dot Kelvin. We just calculated that using Hess's law. So now, the only way that this thing could be that it could be thermodynamically favorable or spontaneous is if the overall entropy of the surroundings went up. So let's take a look at what that actually is. So delta S of my surroundings, remember last time we did it as Q over T, but since we did define that my enthalpy values are equal to that Q value, we're going to go ahead and do this, where we've got that delta H of the surroundings divided by the temperature of the surroundings. And what we're going to do is we'll just plug in these numbers. So 572 joules, actually that's kilojoules per mole, divided by 298. We're going to assume room temperature. We're going to let it come back down. And what this does do is it equals to 1.92 kilojoules per mole dot Kelvin, right? And that's actually, since we're going to convert, because this is another thing we need to watch out for is these units. I'm going to go ahead and convert this to 1920 joules per mole.Kelvin so that these actually line up. So now we get back into this situation where we're doing the delta S of my universe, right, which is the one that actually determines spontaneity, is equal to the entropy change of my reaction plus the entropy change of my surroundings. And when we plug in these values, we see that the overall entropy of the universe is going to go up, right? And so that's why, even though the entropy change of my overall reaction is a negative value, there was enough heat released to the surroundings to make the spontaneity happen, to increase the entropy of the surroundings enough so that I ended up with a 1593, I think is what this ends up being, mole.Kelvin. And so the delta S of the universe did actually go up, and that positive value, that's what determines whether something is spontaneous or not. So again, why did we start with enthalpy? Why did we start with these delta H values? Because that's talking about this energy exchange between reaction and environment. And that energy exchange, just like we looked at when we were doing just our conceptual understanding of what entropy is, then we're saying, hey, is it gaining energy? Is it losing energy? Right? If the temperature of something goes up, the entropy increases. And so now we're starting to apply the math to that, and you'll see why it was important for us to understand what those enthalpy values were and how to define them. All right? And so what we need to understand is it is this thermal exchange, right? That's determining spontaneity. If the overall entropy of the reaction increases, but the entropy of the surroundings goes down even more, then we can still end up with a non-spontaneous or non-thermodynamically favorable reaction. So what we need to understand, and what I would write really big across my screen right now, is that thermodynamic favorability is a function of both delta H and delta S, all right? And I'll repeat that for you, right? That thermodynamic favorability is a function of both delta H and delta S. I would make sure I get that down and I understand that, because we're about to go through a derivation here, okay? So the delta S of my universe, or the total, is greater than 0. That makes something thermodynamically favorable or something spontaneous, right? Now, we're just going to go through the process here. That's the same thing as saying the delta S of my reaction plus the delta S of my surroundings is greater than 0. It is still thermodynamically favorable. All right? Again, just to substitute things in, I will do delta S of my reaction plus delta H of my surroundings divided by the temperature of my surroundings. Again, if these values are greater than 0 when I add them together, I'm still doing I still have a thermodynamically favorable process. Now, something here that we need to understand as well is that everything becomes thermodynamically or reaches a thermodynamic equilibrium, right? When we drop that hot piece of copper into the water, we understand after we let it sit there for long enough that the temperature of the copper in the water is actually going to reach that thermodynamic equilibrium. They're going to be the same temperature. And so when we let these temperatures of the reaction and the surroundings actually reach a thermodynamic equilibrium, we understand that they are equal to each other, right? We also understand in this particular case that the delta H of my reaction is equal to delta H of my surroundings, all right? Because what I'm going to do is I'm going to substitute some things in here. So now I've got delta S of my reaction plus delta H of my reaction and the temperature of my reaction that it's occurring at. And again, same thing, if these values are greater than 0, and I messed up the sign here, that should actually be a minus sign because we made it a minus, right? Because of this value over here, that becomes a minus. And so if these overall, when I calculate those, if the number is overall greater than 0, I'm still in that spontaneous region, that thermodynamically favorable region. And now I'm just going to move a couple of the variables around. I'm going to get rid of that temperature on the bottom, and so I'm going to call temperature times my delta S minus delta H as long as, again, that's greater than 0, I'm still spontaneous. Now, another way to write this, ladies and gentlemen, and I know I'm going through a lot of just different variations of this, but all I'm going to do now is I'm going to flip it, and this is going to be the final one that we're actually going to use. And so if I have delta H minus temperature times my entropy, and these values, notice since I've flipped the negative sign there, they need to be less than 0. Right? If this value is less than 0, we are going to define a process as spontaneous because the enthalpy value has caused an increase in entropy either in the reaction or in the surroundings, and the entropy values itself have created a situation where the overall entropy change of the universe is a positive value. And this is what we are actually going to define. This value from this equation is actually Gibbs energy. So that's what Gibbs energy is, and that's why we say that delta G, right, and Gibbs energy is defined as a delta G value, okay? So that's why we define that overall delta G as the overall end-all, be-all determinant of spontaneity or thermodynamic favorability, because it takes into account both my enthalpy and my entropy changes within a system and its surroundings to make sure that I come up with an overall negative or overall positive entropy increase in the universe. All right, and so this is how we're going to see it over and over. Delta G is equal to delta H minus T delta S. That is Gibbs equation. And as long as Gibbs is less than 0, right, that it's a negative number, the overall entropy of the universe is increasing, the reaction is spontaneous, all right? And so again, let's just go back to our example with our water, and let's plug in our values here. I know my enthalpy value is a negative 572 kilojoules per mole, right? That was given in the equation itself. So minus 298 Kelvin, we're going to assume it's at room temperature. And then here's where it gets a little bit quirky, ladies and gentlemen. I know that my value of entropy was a decrease. It was a negative value, but it was joules, and I need these units to be in kilojoules. You are always, I'd put a star right here and you're always going to have to convert your units in your entropy values to kilojoules, and that would be kilojoules per mole dot Kelvin, all right? And so it'd be 0.372. When I multiply all this stuff together, just to give you the final answer here, I end up with a negative 461 kilojoules per mole. And again, since this is a number less than 0, I'm understanding that the overall entropy of the universe is increasing, and according to the second law of thermodynamics, this is a thermodynamically favorable or a spontaneous process, all right? And so the reason we use delta G is it just simplifies our lives, ladies and gentlemen, where we don't have to do all the individual enthalpy and entropy calculations to actually come up with and predict whether something is going to be thermodynamically favorable, okay? All right, I know that was a lot too, ladies and gentlemen. If you have questions, get them down. I'll see you in tutorials, and other than that, I will see you in class.